Hi, thanks for joining me today. I'm going to be looking sort of at a classic problem in numerical analysis. This actually comes straight from the numerical analysis course at Oxford, so shout out to them, I guess. This is the problem I have. We have P, a polynomial of degree at most n, so that's what this notation means. P is a member of pi n. Okay, suppose we have P of xi equals P of I for I equals 0, 1, all the way through n. In other words, we have these n plus 1 data points, which I've labelled x0, x1, all the way through xn, and we know what p is evaluated at each of those, and I've just called that pi. Now, our problem is, can we determine pn, and is it unique? Okay, so can we find a polynomial p which has these properties, that it is firstly it's a polynomial of degree at most n, and p of xi equals pi for each of these i's here. And also, is that Pn unique? Today I'll be answering both of those problems. So yeah, let's get stuck in. Okay, so the answer to both those questions is yes, we can determine Pn and it is unique. Now, to prove that it's unique, I could use a van der Waals matrix, and we know that van der Waals matrices are invertible, but that doesn't actually tell us what Pn is. But today I'm going to be deriving a Pn and then proving that it's unique. Okay, so firstly let's derive a Pn. So to do that, I'm going to firstly define this this polynomial here. I'm going to call it Li of x, and it's going to be equal to x minus x0 times x minus x1 all the way up to x minus xi minus 1, and then we're going to skip the ith term, so we're going to get x minus xi plus 1, and then we're going to continue all the way up to our last data point, so x minus xn. Okay, now notice that this thing here is a polynomial of degree n. Why is that the case? Well, we've got n different factors here. We've got n plus 1, but then of course we're not including the ith term, sorry. So we've got n factors, each of which are linear functions of x. So this thing here is going to be a polynomial of degree n, and then I'm just going to divide by a constant. So of course that's not going to change the degree. And the constant I'm going to divide by is xi minus x0 times xi minus x1 times ... all the way up to this thing here, xi minus xi minus 1, then xi minus xi plus 1. So again, we're skipping the ith term, and that makes sense because otherwise we'd be dividing by 0. And then we're going to go all the way up to the end, so that's xi minus xn, like so. Okay, so it's essentially the top thing here, but plugging in xi. Now the reason I've done this is, let's note a few things about this polynomial. Firstly, it's degree n, which is great, but also if I plug in xi, then I get 1. Because obviously if I plug in xi, the top becomes the exact same thing as the bottom, so I get xi minus x0, which will cancel with that, xi minus x1, which will cancel with that, all the way through, each of them will cancel, so I'm just left with 1. But also, Li of xj, where j does not equal I, is equal to 0. Because if j does not equal I, then on the top I've got an x minus xj. So of course when I plug in xj, I'm going to get an xj minus xj on the top, so a 0 on the top. So of course it's 0 times something, and of course that's 0. So I can conclude that Li of xj is equal to delta ij, where delta ij is Kroneker's delta. So this thing here is 1 when I and j are the same, and 0 when I and j are distinct. Okay, so now let's use this to construct our Pn. Okay, so I claim that this Pn is a valid solution to our problem, i.e. this Pn here is firstly a polynomial of degree at most n, and also it has the property that whenever you plug in any of the data points, you're going to get that pi out. So if I plug in xi into this thing here, I'm going to get pi out. Okay, let's check that. Firstly, is it a polynomial of degree at most n? Well, yes, because remember we checked that each of the li's are a polynomial of degree at most n, and because we're just summing up a bunch of polynomials of degree at most n, then of course the result will be a polynomial of degree at most n, and notice that this pi term doesn't really affect that because pi is just a constant. Of course it may turn into a polynomial of degree less than n, but that's fine, it's still a polynomial of degree at most n. Okay, so that's that condition done. Now let's just check that it's pi at each of the data points. So in other words, Pn of xi is equal to pi. But let's check that. So Pn of xi, let's just use j instead, is the sum from I equals 0 to n of pi times li of xj. But remember this property here that we just showed, Li of xj is delta ij, so in other words, it's only 1 when I and j are the same. So let's just rub this out for delta ij. Okay, so this, of course, is going to be adding up a bunch of zeros, except in the case when I equals j. So this thing here is equal to pj times 1 plus a bunch of zeros, but in particular that is just pj. Okay, so we've shown this property here. In other words, our polynomial here of degree at most n equals the data points we had when we plug in each of the n plus 1 data points xj. Okay, so we found a polynomial that interpolates the one that we're looking for. It's a polynomial of degree at most n, and Pn of xi equals pi for each of the n plus 1 different data points xi. Now all we need to do is show that this polynomial here is unique, and then we're done. Okay, so the last step now is to prove that Pn is unique, and to do that we're going to prove it by contradiction. So suppose Pn isn't unique. Okay, so let's say that there's Pn and some p tilde n. Don't know why I've written and like that. Pn and p tilde n, and I claim that it has both the properties, i.e. Pn and p tilde n are both polynomials of degree at most n. So let's write that here. Pn, comma p tilde n are polynomials of degree at most n, and also Pn of xi is equal to p tilde n of xi, which is equal to pi. And that's for each of the n plus 1 data points xi. Okay, well now let's consider the polynomial d of x, which is going to be equal to Pn of x minus p tilde n of x. Okay, so the d stands for difference. Now notice this thing here is also going to be a polynomial of degree at most n, because this thing here is a polynomial of degree at most n, as is this one. So when we're looking at the difference, it's still going to be a polynomial of degree at most n. So we know that d is also a member of pi n. Great. Now let's plug in each of the data points. So d of xi, now that's of course just by definition going to be Pn of xi minus p tilde n of xi. And that each of these things here are pi, so we get pi minus pi, and that is equal to 0. And of course that holds for I equals 0, I equals 1, all the way up to I equals n. Okay, so we've shown that d has at least n plus 1 roots, namely x0, x1, all the way up to xn. But remember we had that d was a member of the polynomials of degree at most n, and now by, I guess, the fundamental theorem of algebra, a polynomial of degree at most n has at most n roots, but we've just shown it has n plus 1 roots. So the only way, it has at least n plus 1 roots. So the only way that's possible is if d is the 0 function. Okay, so we can conclude that d is identically 0, but then of course by definition we then get that Pn is the same as p tilde n. And thus our uniqueness proof is done. And that's the end of the problem. So I firstly constructed a Pn, which has the condition that it meets Pn of xi equals pi for each of the xi's, and also Pn is a polynomial of a degree at most n, and then this uniqueness proof proves that it's unique. Of course, as I said at the start, I could use a van der Waals matrix to do this, but this of course requires knowledge of the determinant of the van der Waals matrix, but that's, I guess, is another way to solve this problem. Anyway, I hope you have enjoyed this video. If you are new here, please do consider subscribing. I make lots of fun videos, proofs like this, problem solving, all that sort of fun math stuff. So yeah. Anyway, if you are having a good day, have a good day. If you're not having a good day, I hope this has made it better. Don't know why I said that. I'll catch you in the next one. Have a great day.